The next subtitle is Archimedes' Principle. Any object which is partially or totally submerged in a liquid has a buoyant force acting on it, which pushes the object up. And the force, this buoyant force, is equal to the weight of the displaced liquid. So the famous Greek mathematician Archimedes developed a principle which describes this around 250 BC. Archimedes' principle can be stated as any object completely or partially submerged in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the body. So, buoyant force is equal to the weight of the displaced liquid. When we immerse regular or irregular object into a fluid, there is a displaced fluid. When we measure the weight of the fluid, we get a certain value in Newton, so that is equal to the buoyant force. Or it is possible to find that we know that the weight of the fluid is mass of the fluid multiplied by the acceleration due to gravity. So mass of the fluid is rho of the fluid multiplied by V, the displaced volume of the liquid, and multiplied by. Therefore, in order to find the buoyant force, it is possible to multiply rho of the fluid multiplied by the volume of displaced liquid multiplied by acceleration due to gravity. So the magnitude of buoyant force and is the weight displaced. This shows the relation between the two. So now let's go to the next slide. The reason for this is that the pressure of a fluid is dependent on the depth of the fluid. So when you go down to the ocean, or for example we start from the surface of the ocean, and when you go down, then you will have a different value in the pressure of the fluid. So the reason for this is that the pressure of the fluid is dependent on the depth of the fluid. So the pressure at this point, for example in this diagram, you can see that the pressure at this point is different from the pressure at the second point. So the pressure at this point actually is equal to the H1 rho times G. The pressure at the second point is H2 rho times G. So when you compare H1 with H2, the other variables are the same. So H2 is greater than HY. Due to this, we will get a larger value. So this one, the pressure at the top of an object, at the top of this object, is less than the pressure at the bottom of the object, at this bottom. So the pressure at this point is less than the pressure at this point, which means the force at this point is less than the force at this point. The force 1 at this point is calculated as pressure 1 multiplied by the area. So pressure 1, which is H1 rho times G, and the area. So the force at the bottom of this object is which is represented by F2, which is equal to P2 times area, which is equal to H2 rho times GH, which is a pressure 2 multiplied by the area. Even if the area is the same, so due to the difference in H1 heights, which is H1 and H2, we will get a difference in the values of F1 and F2. Okay, now let's see the first this picture. So this one, when we measure this object in air, we will get 7 pounds. So when you measure, or after we fully immerse this one into this liquid, we get 4 pounds. So from this we can understand that. Actually this 4 pound is the apparent weight. And if you are asked to find the buoyant force, which is the upward force, it's first you have to take the weight of this object in air, which is 7 pounds. So 7 pounds minus this one, the second one, which is the second reading, which is 4 pounds, which is equal to 3 pounds. So the buoyant force is 3 pounds. So when you weight the displaced liquid, we will get 3 pounds of this displaced liquid. So with this we can summarize the force which is applied into this one. Okay, so having this in mind, now let's go to the other slide. The other slide contains an example. It says that a sample of unknown materials weight in air is 300 Newton. and this is unknown material, and in 200 Newton when it's submerged in alcohol solution. Like the previous example, when you submerge into the alcohol solution, you get this mass amount of Newton. And the raw value of this alcohol is 0.7 times 10 raised to 3 kilogram per meter cubed. So now we are going to find raw value of this unknown material, and I will show you this step by step. To solve that question, we can consider this one. When we measure the weight in air, it is 300 Newton. Weight in air is 300 Newton. Weight when we immerse into the alcohol, the weight is 200 Newton. So this one, or the displaced, due to the displaced liquid, there is a buoyant force Fb, which is upward. So to get the buoyant force, we can subtract 200 from 300. But before that, let's calculate this one. The weight in air is 300 Newton, which means weight of the object, which is equal to mass of the object multiplied by the acceleration due to gravity. Therefore, if you want to find mass of the object is equal to weight of the object divided by the acceleration due to gravity. Weight of the object is over gravity. Weight is 300 Newton and gravity 9.8 meters per second. So when we divide this one, 300 Newton divided by 9.8 meters per second, we will get 30.61 kg. Now we have got this weight. Then after this one, we are going to find the volume in order to find rho of this object. So the unknown value is rho of this object is unknown. In order to find this rho, we need mass of the object and the volume of the object. So in order to find the volume of the object, first we have to know the buoyant force. The buoyant force, which is equal to the weight of the displaced liquid, which is equal to 300 Newton minus 200 Newton. 300 Newton minus 200 Newton, which is equal to 100 Newton. So this 100 Newton is equal to the buoyant force, which is equal to the weight of displaced liquid. Okay, so weight of displaced liquid, which is equal to the buoyant force, which is equal to 100, is equal to mass of the liquid times gravity. And we know that rho of the liquid is equal to mass of the liquid divided by volume of the liquid. So mass of the liquid is equal to rho of the liquid times volume of the liquid. Now replace this mass of the liquid with this one, and we'll get rho of the liquid multiplied by volume of the liquid multiplied by gravity is equal to 100 Newton. So divide both sides by rho of the liquid and the acceleration due to gravity, will get 100 then divided by rho of the liquid multiplied by acceleration due to gravity, and we'll get the volume of the liquid. Now we have rho value, and this one is given 100 Newton, and this is constant. Rho of the liquid, it's already given, which is equal to 0.7 times 10 raised to 3 kilogram per meter cubed multiplied by 9.8 meter per second square, which is equal to volume of the liquid. So finally, the volume of the liquid will be equal to 0.01457 meter cubed. Now we have volume of the liquid. Volume of the displaced liquid is equal to volume of the object inserted into the alcohol solution. So then the next step is just to find rho of the liquid. Rho of the object, which is equal to mass of the object over volume of the object. You know that volume of the liquid, the displaced liquid, is equal to volume of the object. Therefore, rho of the object is equal to first we have to take mass of the object, which is 3.0 30.61 kg divided by the volume of the displaced liquid, which is the volume of the object, 0.01457 meter cubed. So when you divide this one, we'll get the result, which is equal to the result is, when you divide this, the result will be 2099.883 kg per meter cubed. So we rewrite this one, it becomes 2.001, approximately 2.01, or not 2.01 actually. This is equal to 2.1 times 10 raised to 3 kg per kilogram per meter cubed. This is the answer. Okay, above all, now let's see the fluid dynamics. Okay, which is different from the previous one. In this case, we consider fluid in motion. So we have this equation of continuity. Bernoullis equation will be included under fluid dynamics. So there are many categories of fluid in motion, categorized by whether the fluid flow is steady, not steady, compressible, incompressible, viscous, or non-viscous. Okay, as you can see, the study of liquid in motion, we can call it hydrodynamics. So an incompressible flow is the flow of fluid which cannot be compressed. So most liquid are nearly incompressible, and in most calculation we consider the liquid to be incompressible. So a viscous fluid is one which does not flow easily, a viscous fluid, and like honey, while a non-viscous fluid is one which flows more easily. This is an example for non-viscous fluid. So the various layers of a fluid slide smoothly past each other. So this is called streamline or laminar flow. When it is smooth, there is also turbulent flow. I can show you this in the next slide. So this next slide shows the laminar flow and turbulent flow. So this laminar flow is characterized by a smooth and regular path. This path is the path followed by the particles. The particles of the fluid is very smooth and it's regular. But when you see the turbulent flow, it is characterized by irregular movement, not regular, irregular movement of these fluid particles. So the fluid particles will move one in a curved path like this, and so some of the fluid particles is rotate just like this one. So due to this, we get a turbulent flow or irregular movement of the particles. So these are the two important pointers. Okay, so when you see the other one, the factor affecting the laminar flow, the previous one, so rho is 1, and the compressibility, temperature, and viscosity of the fluid, 3 of them affect the laminar flow. And the other very important point is this one, which is an assumption made for in the ideal fluid flow to understand the complex motion of real fluid. So in order to understand, some of the points should be assumed. That is, the fluid is non-viscous. Whenever we solve some questions, we consider that the fluid is non-viscous. There is no internal friction between adjacent layer. This is one of the consideration. The other consideration or assumption, the flow is steady. The velocity of the fluid at each point is remain constant. This is the second assumption. And the third assumption, the fluid is incompressible, and rho value of the fluid is constant. So the number 4, the flow is irrotational. So in this case, we don't need to consider the angular momentum about any point. So these are the 4 of the important points whenever we solve different question in fluid dynamics. Okay, having this in mind, now let's see the equation of continuity. And this equation of continuity expresses the conservation of mass for an incompressible fluid flow. in a tube. So it says that the equation of spontaneity, the amount of fluid flowing through a cross section of a tube in a given time interval, we have to consider the time interval, must be the same for all cross sections. So whether the tube is narrow or wide, so the amount of fluid or the volume of fluid which passes in a given time interval is the same for narrow and wide. So, or the product of area and the fluid speed at all points along the tube is constant for compressible fluid. I can show you this using. Okay, now this is a flow rate. Now let's consider the tube with smaller area A1 and larger area A2. So in case of this smaller area, let's consider the volume V1 and V2, and we have area 1 x1 and area 2 x2. So the same volume flow in the same time interval. Therefore, in this time, the time interval taken to be t1, let's say this is t2. So this time interval, the v1 is equal to v2. The volume v1, which will be acquired in a given time interval, will be the same as the volume v2, and t1 must be equal to t2. T1 is taken to be equal with t2. Therefore, volume 1, this volume is calculated as area 1 multiplied by x1, multiplied by this one, which is x1. And the second volume, this one, is calculated as area 2 multiplied by x2. So area and x1, we know that distance is measured as distance. Let's say x is the distance measured as v times t. So when you say this one is x1, for x1 we have v1 and t1. For x2, distance 2 is equal to v2 t2. Therefore, now let's substitute x1 and x2. Area 1, x1 means v1 t1. Area 2, x2 means v2 t2. We know that t1 is equal to t2. T1 and t2 are the same. Therefore, we can cancel out this one, and finally we'll get area 1 v1 is equal to area 2 v2, which is equal to the flow rate. While flow rate is A times V, or area 1 v1 is flow rate, A2 v2 also, because they are the same value. So with this we can get the equation of continuity. I think that is V is equal to A1 v1 and to v2. Therefore, in general, the condition AV, which is equal to constant, equivalent to the statement that the volume of the fluid that enters in one end of the tube in a given time interval equals the volume leaving the other end of the tube in the same time interval, if no leaks are present. So flow rate is equal to volume over time, which is AV, which is equal to constant. Okay. So now the next or the last part of chapter 3 is regarding the Bernoullis equation. So in 18th century, the Swiss physicist Daniel Bernoulli drew a relation between velocity of a fluid and pressure it exerts. Qualitatively, Bernoullis' principle stated that swiftly moving fluid exerts less pressure than slowly moving fluid. So Bernoullis equation is really a consequence of fundamental principle of physics, that it talks about the conservation of energy. It can be derived using energy principle. So Bernoullis have got a relation which is P plus 1 over rho V square plus rho GH is equal to constant in all points, based on the conservation or the principle of physics, which is the conservation of energy. So energy is conserved. So in different points. So consider a fluid moving through a pipe. The pipe cross-sectional area changes and the pipe elevation also changes. So in this case, we need to apply the Bernoullis equation. So at one point of the pipe has a cross-sectional area, let's say A1, and height AY1, and a pressure P1 and the velocity V1. moves a distance a given time. So another point, maybe at the second point, let's say this is the first point, that is we consider P1, A1 and V1 at Y1, and the other one is at Y2. So in this case we have P2 and A2 and V2. So A2 V2 I2 P2 V2 is considered. So conservation energy gives the following equation. So from the conservation of energy we have got that the pressure at a given point plus 1 over 2 rho v square at that point plus rho times g times y is always constant. You can take the point A here, another point here, wherever you take, this value is constant. So if you take point 1 and point 2, you can say that this is P1, rho times V1, rho is the same, acceleration due to gravity is considered to be the same, times Y1 for one case, and for the second case P2 plus half rho V2 square plus, so these points are the same. If you have third point, you can say that P3 is equal, this is equal to P3 plus half times rho times V3 square plus rho times g times y3. So we proceed like this. Okay, so there is an example. A water circulates through a house in hot water heating system if the water is pumped at the speed of this one through a 4 centimeter diameter pipe in a basement under a pressure. So what will be the velocity of and pressure? 2.6 centimeter the diameter pipe on the second floor. The second floor is at height of 5 meters. So first we have two important points that is listed in this question. So this one, the speed, this one is v1, the speed one, and so there is a water, so the rho value is known, rho values of the water we have to take, and the other one is the diameter. The diameter of the pipe here is 4.0 centimeter. The diameter there is 2.6 centimeter. So we know that from equation of continuity, we know that A1 V1 is equal to A2 V2. So that will be applied on this question. When you describe more from the diameter, it's possible to get the radius because this diameter divided by 2 is the radius. Therefore area is equal to pi r square. That is how we get the area, or pi r square means area 1 is equal to pi diameter over 2 the whole square. So diameter of the first one is known, which is 4.0 centimeter. So divided by 2 and the whole square multiplied by pi, we'll get area 1. For area 2, the diameter is given 2.6. Therefore area is equal to pi r2 square, which is d2 over 2 the whole square. So with this we can find area 1 and area 2. And v1 is already given from this relation, and v1 is 0.5 meter per second, but h1 is 0 meter. It's the water pump is this one and basement, so the basement is 0, but h2 is 5 meter, which is the second floor. Second floor is okay. So the pressure 1, which is equal to 3.03 times 10 raised to 5 Pascal. So pressure 2 is not. Now when you see the solution, we don't know this V2 and P2. So from the equation of continuity, A1 V1 is equal to A2 V2. So V2 can be easily calculated by this equation of continuity. A1 is given, A2 is given, V1 is already given. So finally you'll get the V2 value, which is 11.83. And now we apply the Bernoullis equation, which is P1 half rho V1 square plus rho GH1, P2 plus half rho V2 square plus rho GH2. So the unknown, that the first unknown that we need to know here is the P2. Therefore P2 will be equal to P1 plus half rho V1 square, this one, rho GH1, this one, minus of, we have to take this to the left side. When you take this to the left, it become negative rho V2, and when you take this from the right to the left side, it become negative rho GH2. So this is v1 and this is v2, so it becomes 1 over rho is common, therefore v1 square minus v2 square. And when you see this h1 and h2, rho g is the same, rho g h1 minus h2, rho g h1 minus h2. Okay, so now substitute the value. This is P1, the pressure, 1 over 2, and this is the rho, which is 1.010 for water, and V1 square, this is V1 square and V2 square, so meter per second square, and rho of the water times acceleration due to gravity 9.8, and H1 minus H2, which is 0 minus H2. Second one is the first one is 0, the ground, so, and the second floor, which is at you can find second floor at 5 meter. And finally, you will get P2 is equal to 1.84 times 10 raised to 5 Pascal. So this is the end of chapter 3. So that's enough, and we will have more